welcome to CEC lectures. Myself Dr. Priti Jagwani from Department of Computer Science, Aryabhat College, University of Delhi. So in this present series of artificial intelligence, in our initial lectures, we have looked into what actually artificial intelligence is and what is going to be the motive behind this particular course. That is the study of rational agents, and then we have looked into what all type of intelligent rational agents are available and their types. Now today's agenda is about if we need to solve some problems, what are going to be the different strategies for solving problems in the domain of artificial intelligence. So the first strategy which we are going to look onto is searching. So today's topic is solving problems by searching. So when we say solving problems by searching, that means your agent is actually looking ahead in order to find out a suitable sequence of action that will eventually achieve its goal. So when the correct action is when the correct action to take is not the immediately obvious, an agent may need to plan ahead, that is to consider a sequence of action that form a path to a goal state. So that means from initial state to goal state, what all are going to be kind of the actions, which sequence of action is going to lead your agent to the goal state is actually your and what we can say is search. So such an agent is called a problem solving agent, and the computational process which I was just describing, or I can say the process which your agent is going to undertake in order to reach the goal state is called the search. So here we are going to deal into problem solving agents and the computational process which they are going to kind of execute, or which they are going to implement, and that is what the search is. Now when we say problem solving agent and the search, one thing which we need to be very careful about the representation of the state. So please recall that we have seen three representations of various states. One is atomic, another one is factored, and third one is the structured. So here your problem solving agents use atomic representation, that search is state of the world are considered as a whole. That means they are atomic and they cannot be divided into kind of different parts. Actually no internal structure is visible to the problem solving algorithm. So this is what we can say kind of an atomic representation. And when we are talking about problem solving using search or the search techniques, we are specifically talking about the atomic representations, because when are we going to deal into the factored or the structured representation of states, then the agents, those agents who are going to use factors or structured representation of states are basically planning agents, that they are not they are not dealing in search, or we can say simply that they are not kind of searching agents. So here we are actually if you can see, we are considering only the simplest environments. In the sense, simplest environments, when we talk about, we have seen properties of environment. So the environment which we are considering here is episodic, not sequential; single agent, not the multi agent; fully observable, not the partially observable; deterministic, not stochastic; statistic, not dynamic; discrete, not continuous; and known, not unknown. So the simplest of all the environments: episodic, single agent, fully observable, deterministic, static, discrete, and known. This type of environment we are going to consider when we talk about this problem solving using problem solving agent and the agents which are actually relying on the search techniques. Now if we talk about types of search techniques or types of algorithm, we can have here the informed algorithm or the uninformed algorithm. So informed algorithm, when we talk about, the agent can estimate that how far it is from the goal. So, at a particular state or even at the initial state, what is the distance between that particular state and the goal state, that can be estimated somehow. Now, how these are going to be estimated, that is altogether a different kind of dimension. Definitely we are going to look into that as well, but now not in this lecture, because that is actually out of scope of this lecture. So, we need to distinguish between informed algorithms and uninformed algorithms. So, informed algorithms in the sense in which your agent can estimate how far it is from the goal, and uninformed algorithms when no such estimate is available. Also, if the agent has no additional information, that is your environment is unknown, then the agent can do no better than to execute one of the actions at random, because agent is having not having any idea that how to reach to a particular state or which is the better move to opt for. Then in that situation the agent can do no better than to execute any of the actions at random, and we are assuming that the agents always have access to the information about the world also. Now, with that information about the world, the agent can follow a 4-phase problem solving process, that is the problem solving using search techniques. Now, what are the 4 phases of this problem solving process? So, the first phase is formulation of goal, which is goal formulation. The second phase is problem formulation, that means kind of coining the whole problem. Then search, which is kind of looking for the option to reach to the goal state, and finally the execution. So, the 4 phase process: goal formulation, problem formulation, search and execution. Now, let us see this 4 phase problem solving process in detail. So, when we talk about, let us say, goal formulation, so the let us take the example of route planning, and the agent adopts to adopts the goal of reaching to a particular place, let us say kind of B or any particular city. Now, goal organize behavior by limiting the objectives and hence the actions to be considered. Now, your agent after this goal formulation is having a specific goal in having a specific target, which is able to because of which your agent is able to organize the behavior. Moving forward, the stage of problem formulation comes up. Here in the stage of problem formulation, the agent devises a description of the states and actions necessary to reach the goal, or we can say this is actually an abstract model of the relevant part of the world. Relevant part as in whatever part is kind of is of importance to that particular agent, but here we are talking about not the concrete model, but the model in the abstract sense. So, here your agent is going to look for a description of all the states and all the actions which are necessary to reach the goal. Now, for example, if we are talking about that scenario of route planning, one good model is to consider the actions of travelling from one city to an adjacent city, and therefore, the only fact about the state of the world that will change due to an action is the current city. So, your agent is going to move from one city to whichever adjacent city is available, and what is being kind of being changed here due to an action is actually the current city. So, presently let us say for example, the current city is A and it is going to move to city B under a particular action which is move A comma B. So, now the current city is going to be the B. So, the change due to this action is going to be the current city. So, actions and the states it has formulated under this phase of problem formulation. Moving forward, now states are kind of we can say seen, so are actions. But before taking any action in the real world, your agent actually simulates the sequence of actions in its model, searching until it finds a sequence of action that reaches the goal, and such a sequence is called the solution. So, basically in this process or in this phase of search, your agent is actually simulating actions, sequence of actions in its model. So, simulation is happening within the model, and that simulation is going to look out for a particular sequence of actions which through which your agent can your agent will be able to reach the goal. Now, agent might have to simulate multiple sequences that do not reach the goal, but eventually it is going to find a solution. So, that means there are so many paths, or there are so many ways available. So, your multiple sequences are available. Out of those multiple sequences, many will not reach the goal, but eventually your agent is going to find a particular solution. So, for example, such as going from A to B, then from B to C, then from C to D. So, a particular sequence is formed, and let us say D is your the goal state. Or it is also possible that it will find that a solution is not existing, or we can say no solution is possible. So, either from the multiple sequences, either your agent is going to find one solution eventually, or it will find no solution possibility. Now, in case of the fully observable deterministic known environment, that means the environment which we are considering, the important property is that the solution to any problem is going to be the fixed sequence of actions, because your environment is fully observable and it is deterministic and already a completely known environment. Then the solution here in this case of environment is going to be a fixed sequence of actions. Now, another concept which we need to look is that this process is actually either it is open loop versus closed loop. So, once the agent has found a solution, please remember that only the solution has been found, it has not been executed yet. It can ignore its percept while it is executing the actions. That means closing its eyes, so to speak, because the solution is guaranteed to lead to the goal. So, the solution is already there. Now, there is no need of the percept, or there is no need of more interaction with the environment in order to get the new inputs while it is executing the actions, because agent has already found the solution and that solution is guaranteed to lead to the goal. So, control theorists call this kind of an a system is an open loop system ignoring the percept, which breaks the loop between the agent and the environment. So, we need to ignore the percept because we do not want to break the loop between agent and the environment. Now, but on the other hand, if there is a chance that the model is incorrect or the environment is non-deterministic, then from the agent's point of view, it is always a safer idea to use a closed loop approach that monitors the percept. That means it is not ignoring the percept in this situation. Your agent is actually we can say it is taking the percept into the consideration, and this happens when there are the chances that your model could be incorrect, or we can say the environment is non-deterministic, or your environment is stochastic in another way. Then for agent it is a safe idea to follow this closed loop approach in which the percept is also monitored. In partially observable or non-deterministic environment, a solution would be a branching strategy that recommends different future actions depending on what percepts arrives. Now, with these properties of open and closed loop, we have seen that how this is going to this 4 phase are going to be there. So, first is a goal formulation, then there is a problem formulation, then searching for the solution, and finally executing that particular solution which has been found in step number 3. With the help of these 4 phases, we can coin, or your agent can coin, well defined problems and their solutions too. Now, what are the components through which your problems can be defined formally? So, there are 5 components: initial state, actions, transition model, goal test and path cost, and we have seen all these 5 components in the previous lecture along with the various examples, and the examples which we have considered. Let me help you recall that the toy problems, which was the 8 tile puzzle problem, and that we have also seen that all these 5 components of a well defined problem in using the example of vacuum cleaning world. So, initial state from which your agent is starting, actions you all understand, that is how the state is going to be changed by which particular movement or something of that sort. Transition model is what is the state, what is the current state, what action we are going to take, and what is going to be the next state. So, from let us say we are at A, we are going to move to B, and then finally your current state will be B. So, that completes as the transition model. Whether whichever state you have arrived or your agent has arrived on, whether that is a goal state, yes or no, that is being done in goal test. And then finally, what is the cost of that particular path using which you have attained the goal state. So, from initial state to goal state there is a path, and what is going to be the cost of that particular path, that comes under the component of path cost. So, a problem can be defined formally by using these 5 components, and this we have already we can say we have covered in our earlier problems. Moving to our next module after this is that is known as a constraint satisfaction problem, or in short we commonly call it as a CSP. So, when we say constraints, constraint means you need to follow this particular condition, you cannot or you should not disrespect this condition. So, for example, let us say we are taking a factored representation for all the states. So, when we say factored representation for the state, that means that factored representation is having a set of variables, and each of that variable is having a value. Now, your problem is to be solved with all these variables, and each variable has a value that satisfied all the constraints on the variable. So, for example, there is a variable, let us say x, and this x can be assuming that this is an age or something of that sort. So, this cannot be greater than 100, or this cannot be less than 0. So, this is kind of a constraint, and we need to look into each and every constraint which are put on to the variables, and looking or after respecting those constraints, a problem is to be solved. A problem described in this way, in which we are taking the variables along with their constraints, is called a CSP, which is known as a constraint satisfaction problem. Now, constraint satisfaction problem are actually the search algorithms, we can say, that take the advantage of the structure of states and use general rather than domain specific heuristics in order to enable the solution of the complex problem. So, the idea is to solve the complex problems. Those complex problems are going to be get solved using these constraint satisfaction problems and search algorithms along with, because these CSP search algorithms are going to take advantage of the structure of the states, and they are going to use general heuristics rather than any domain specific heuristics. So, for example, let us again consider this x. So, rather than having an open value for x starting from 0 to anything, it makes a lot more sense that because x is actually a variable which is encoding or which is representing age of a human being, normally it should not be kind of more than 100. So, these are the heuristics which are actually kind of help a particular agent to kind of narrow down the search space, we can say, and this we are going to look into through a particular example in a short while. Also here, if we talk about the constraint satisfaction problem, now what is the bottom line idea or what is the main idea? The main idea, as I was talking about, is to eliminate large portions of the search space at once by identifying the variable or by identifying the value combinations that violate the constraint. So, all those value combinations or all those variable combinations which are going to violate the constraints, we are not going to kind of consider them, we are not going to take them up into the consideration, because we need to look for the solution by also along with kind of respecting those constraints. We cannot just kind of ignore those constraints. So, the main idea here, by respecting those constraints, most of the search space is going to be kind of eliminated, and all those value variables or all those combinations of variables, those who are kind of violating the constraints will not be considered. Now, constraint satisfaction problems have the additional advantage that the actions and the transition model can be deduced from the problem description itself, because whatever the problem description is given, your actions and the transition models can be kind of, we can say, derived from there. Now, let us try to kind of define a constraint satisfaction problem in a formal manner. A constraint satisfaction problem consists of three components. One is x, another one is d, and third one is c. So, x here is actually a set of variables. Let us say there are n variables. So, starting from x1 to xn, x is actually a set of variables. Coming to the set d, which is the set of domains starting from d1 to dn, and actually here this domain is kind of, we can say, one for each variable. So, for x1 the value, or sorry, the domain is d1, for x2 the domain is d2, and so on and so forth. And looking into the third part, which is c, c is actually a set of constraints that specify allowable combination of the values. So, a constraint satisfaction problem, if we are going to define, we need to have three components. One is x, set of variables, d as in set of domains, and c, which is your a set of constraints that specify whatever combination, whatever variable sets are allowed. Now, any domain di consists of allowable values for a variable xi. For example, if we say there is a Boolean variable x1 and the domain is, for Boolean variable, domain is going to be either true or false. So, the allowable values for a Boolean variable are true or false. So, v1 here, which is the allowed value under that domain di, is true, and v2 here is going to be false. Now, different variables can have different domains of different sizes that we need to take care of. Coming to the constraint, for example, let us say we have a constraint Cj, which consists of a pair which is h of scope and relation rel of I, where relation is a tuple of variables that participate in the constraint, and relation is actually something that defines the values that those variable can take off. So, here once we have kind of a scope, and another one is the relation which we have. So, the relation that defines the value that those variables can take off, and then this relation can also be represented as an explicit set of all tuples of values that satisfy the constraint or as a function that can compute whether a tuple is a member of the relation, yes or no. So, for example, let us try to understand this situation with the help of an example. So, for example, we have x1 and x2 and they both have a domain 1, 2 and 3, but the constraint here says that x1 must be greater than x2. So, then we can say h of x1, x2 can be 3, 1 because x1 here is greater than x2, can be 3, 2 or can be 2, 1, or in a general format it can be written as h of x1 comma x2 where x1 is greater than x2. So, this is how we are going to coin the scopes and the relation using the domains. Your constraint satisfaction problems deals with the assignment of values to these variables along with respecting these constraints. So, any assignment does not violate any of the constraint and that assignment we consider as a legal assignment or a consistent assignment. A complete assignment is one in which every variable is assigned a value and a solution to a CSP is a consistent and a complete assignment. A partial assignment is one that leaves some variables unassigned, and a partial solution is a partial assignment that is consistent. Please remember that solving a constraint satisfaction problem is an NP-complete problem in general, although there are important subclasses of these CSPs that can be solved very efficiently. So, in this lecture, if we kind of recap, we looked into the constraint satisfaction problem, but before going into constraint satisfaction problem, we looked into the problem solving strategies using search, followed by their properties like open loop versus closed loop and so on and so forth. Then we have seen the constraint satisfaction problem. We try to understood the definition, but yet more to be covered in this constraint satisfaction problem, which will be followed in my next lecture. Till then, take care. I will see you in the next. Here is a list of references which is being used for the preparation of this lecture.